Ever since the term artificial intelligence was coined as much a marketing label as a scientific one by John McCarthy in 1956, the anthropomorphizing of this technology accelerated alongside its portrayal as something universally beneficial and desirable for society. Frank Rosenblatt advertised his perceptron model as something analogous to the human brain, with the potential for future reproduction and even sentience. The main unresolved problem that continues to lurk in the background of this field can be traced to the absence of a unified definition of intelligence itself. This inevitably leads to relative measures of progress, benchmarked against human capabilities, the only definitive reference point currently available. The alluring promise of AGI bringing about the fourth industrial revolution due to its purportedly superior general problem-solving abilities might create the impression that the boundary between natural and artificial intelligence is steadily dissolving. It becomes therefore crucial to dissect both categories and their exact differences, to not lose sight of their defining qualities, ideally demonstrated by examining the domains in which each form of intelligence excels, and those in which each still falls short. Here, the three-mass level of analysis will be employed to illustrate the contrast, as intelligence is not only about performance, but inevitably emergent from constraints, internal representations, and processes. Starting in reverse order at the level of implementation, we were asking how computations are physically realized in the first place. In his theory of society of mind, Minsky posited how the material substrate itself, be it carbon or silicon, is of less importance to develop multi-agent systems than its organization and processes. The properties of the substrate begin to matter, however, in non-trivial ways once the constraints they impose are considered. We know that biological brains are built from slower, noisy, and low-precision components called neurons, each of which has around 10,000 synaptic inputs to it, leading to exceptionally dense and recurrent connections with massive parallelism. These physical properties bias the brain towards correlation-based, fault-tolerant, and probabilistic models of computation. Likewise, sensory and associative processing is never cleanly separated, making multisensory integration not an optional add-on but an inbuilt property of the neural hardware. The hippocampal system is the best example here, which receives convergent input from all sensory and spatial processing streams. Their recurrent connectivity enables memory, perception, and action-related representations to continuously interact so that information from different modalities is inextricably bound together. Although recurrence and noise can be engineered into artificial systems, they are not intrinsic organizing principles of canonical transformer-based architectures. Temporal dependencies are typically externalized through attention over stored representations, and noise is introduced instrumentally rather than arising from a system's physical dynamics. These implementational differences consequently constrain the kinds of algorithms and representations that can be realized in the first place. The algorithmic level then asks how information is represented and transformed to produce behavior. Contemporary AI systems, particularly deep neural networks, can best be characterized as statistical function approximators that optimize parameters to minimize an externally defined loss function over large datasets. All internal representations emerge only implicitly as intermediate states that are useful for loss minimization, not because they correspond to semantically grounded entities. In transformer architectures, this information is encoded in high-dimensional vector embeddings, where points represent a token's vector representation at a given layer. Meanwhile, self-attention computes similarity scores between token representations and uses them to dynamically reweight information flow. What appears as reasoning is largely the result of learned statistical structure in sequence space, rather than inference over an explicit world model. Biological cognition, by contrast, operates through recurrent generative models that continuously predict sensory input and update latent hypotheses about the world. The brain is not minimizing prediction errors in isolation, but engages in active inference, selecting action to reduce uncertainty while satisfying physiological and behavioral constraints. The brain minimizes so-called variational free energy, which balances accurate prediction of sensory input with the complexity of the internal model needed to explain it. Perception and action are thus tightly coupled through continuous feedback loops, enabling the brain to maintain latent hypotheses about the world. Representations are conclusively deeply action-oriented and multimodal, shaped by embodiment and survival rather than dataset statistics. These representational commitments also constrain memory mechanisms available to each system. In artificial systems, memory is address-based and explicitly indexed, reflecting the need for stable storage that can be efficiently integrated into optimization pipelines. this at best approximates the content addressable, associative memory intrinsic to biological cognition, where recall emerges from recurrent dynamics and pattern completion. All of these algorithmic choices bring us to the computational level of analysis and the original question of what each system is optimized to achieve, as well as how its notion of successful problem solving is defined. We can infer that current AI is optimized for performance on explicitly defined tasks. The problem space is specified in advance, the relevant variables are pre-selected through data and architecture design, and success is mainly measured by minimizing error or maximizing reward according to a predefined metric. It is in this sense fundamentally instrumental, solving problems for which the objective function is already known. Natural intelligence, by contrast, is optimized for computational meaningfulness rather than task performance alone. The brain does not merely compute which action maximizes reward, but continuously evaluates what is worth attending to, learning about, or acting upon in the first place. This evaluation is deeply context-sensitive and depends on internal models of the world that encode causal structure, function, and relevance. Humans rely on so-called dynamic mental models, sometimes referred to as intuitive theories of physics, psychology, and culture. These models allow us to understand not just what is present in a scene, but how objects function, how agents are likely to behave, and what actions are appropriate within a given social and cultural context. These models are not exhaustively enumerated, but selectively deployed under severe resource constraints. This reflects a form of resource-rational intelligence. Rather than optimizing over all possible states and actions, the brain samples only a small number of highly probable hypotheses and updates them as new information arrives. This is only possible through the use of inductive biases and expectations which lead to relative comparisons between what is essential versus irrelevant. From a computational perspective, the goal is therefore not optimality in a formal sense, but adaptive sufficiency, to behave well and fast enough under uncertainty. Artificial intelligence systems, even when they reach or surpass human-level accuracy on benchmarks, would typically lack such intuitive world models. They are effective at recognition, but weak at causal explanation, scene understanding, and flexible generalization. And while recent approaches do incorporate probabilistic reasoning and Bayesian belief updating, most notably through probabilistic graphical models, these mechanisms reach their bottlenecks when it comes to scaling to the open-ended, context-rich decision spaces humans navigate with ease. Their failures, often in the form of susceptibility to outliers or contextual shifts, are all direct symptoms of a different computational objective, to optimize statistical regularities rather than to construct and aim for meaning. From this perspective, the difference between artificial and natural intelligence is not one of degree, but one of innate computational orientation. The former is optimized for efficient solution of predefined problems, the latter for survival, adaptive learning, and sense-making in environments where the problem itself is almost always uncertain.